In this video, I'm going to walk you through an example of hypothesis testing in a real-world scenario. We're covering independent samples t-test this week, and this is a good example of a research design in which you would use that. So, as you know, the scientific method consists of coming up with questions, developing your hypotheses, formulating predictions, designing and implementing a study, testing those predictions, and then drawing inferences and repeating. In statistics, we've been focusing on testing the predictions, specifically the statistical analyses, but it's easier to understand if you put it in context of a real experiment. As you know by now, the most difficult part of this class is actually understanding the variables, the experimental designs, or the research designs, and interpreting them in plain English. So maybe this will help. So let's start with this example. This question I came up with during the pandemic, and this was a good question, right? Does having the camera on while testing affect student grades for online exams? Now, my two classes from this semester so far believe that yes, it will, and they believe that students will do better with the camera off. Mainly, they said, because that facilitates cheating, which is a pretty bleak view of things, but because there's other reasons, right? Maybe they're just more nervous with the camera on. So how could we test this? So the ideal way would be to randomly assign students within the same class to take a midterm, for example, either with the camera on or the camera off, right? You could also do it at the classroom level, which can be more convenient, right? You could randomly assign 2 courses taught by the same professor in the same semester to have the camera on in their first midterm and off in the second midterm for one class, and off in the first midterm and on the second midterm for the second, to be fair, right? And then you could do a complicated design. But for the purposes of this demonstration, we're just going to assume that we randomly assign students within the same class to take an online exam with the camera on or off. So 2 groups. The camera on would be the experimental group. The camera off would be the control group in this example. This would be a true independent variable because we use random assignment. Our dependent variable in this case is simple, test scores. So we start with our hypotheses. So we will use a non-directional hypothesis here. Students with the camera on will do better or worse on the exam than those with the camera off. Our null hypothesis, as usual, is that there will be no difference or no effect. In this specific example, there'll be no difference between mean exam scores for those with camera on versus those with camera off. Our next step is to spell out our predictions, or the logic of our experiment. What we need to understand is what our data will look like if the null turns out to be supported, or null turns out to be not rejected, right? Or if our alternative turns out to be supported. So if being observed affects performance, if that's our alternative hypothesis, then participants who take the exam with a camera on will do better or worse on it than those with a camera off. In other words, mean exam scores will be higher or lower in the experimental group compared with the control, no camera group. If being observed doesn't matter, in other words, the null hypothesis, then there will be no difference between mean exam scores between the 2 groups. Okay, at this point, we design and implement the study and collect the data, okay? And then we're going to test the predictions. So just to review, our hypothesis testing steps begin with stating the null hypothesis and alternative hypothesis. Always do this before you run your analyses. In this example, the null is that there will be no difference between mean exam scores in the 2 groups. And we write it out like this, okay? H sub 0, mu1 minus mu2 equals 0. Our alternative is that there will be a difference in mean exam scores between the 2 groups. The camera will make a difference. We write this out, non-directional hypothesis, as mu1 minus mu2 is not equal to 0. Our next step is to set the alpha level, or our decision criterion. This just refers to how much risk of being wrong about rejecting the null are we willing to assume. Okay, this refers to the type 1 error rate. How likely are we to make a false positive or reject a true null hypothesis? The standard in behavioral sciences is setting the alpha level at 0.05. This is equivalent to saying or assuming that we would reject a true null hypothesis about 5% of the time. Now, here again is our statistical decision process chart here, right? So if we reject a null hypothesis that is true, this is we're making a type 1 error. It's an alpha error, the one we just assume with our alpha level, right? On the other hand, we could also have a false negative, and we could fail to reject a null hypothesis that is not true in reality, right? This is our type 2 or beta error. Of course, we could fail to reject a null hypothesis that is actually true. This is the correct decision, but not very exciting for the researcher. Or we can be happy researchers and reject a null hypothesis that is actually false, right? This means we have enough power to find an effect. Back to our hypothesis testing steps. At this point, we state our decision rule. If our alpha level is 0.05, then our decision rule is to reject the null if p less than 0.05. Okay, p just refers to the probability of obtaining the data if the null hypothesis were true. At this point, we have to decide whether we're going to use a two-tailed test. Since we made a non-directional hypothesis in this example, we will use a two-tailed test. Okay, in a two-tailed test, our region of rejection, so that 5% is divided in the two tails of the distribution. We'll talk more about the distribution of the differences, the sampling distribution of the differences between the means in the main lecture. Okay. Next, we collect data, and we have to decide how many people. To decide how many people, we use a power analysis, right? So just to refresh your memory, statistical power refers to the probability of rejecting a false null hypothesis. Your power is influenced by beta, which is your type 2 error rate. Okay, 1 minus beta is power. Your effect size, how big is the difference between the means in our example, right? Alpha level. Our sample size, and that's what we're looking at now. We want to use a power analysis to determine the sample size necessary to find the effect that we expect to find. And we base this on past research, okay, and maybe a pilot study and so forth. Power is also impacted by the standard deviation of the population, right? The smaller the standard deviations, the more power you have. So after we determine our sample size, we collect data. We randomly assign students to take the exam with or without the camera on. Because they're two groups of different people, we use an independent sample t-test to analyze the data. All right. So we calculate this test statistic and p-value. In this case, we let SPSS, or actually Jamovi is what I used for this exam, to figure this out. And we refer to our decision rule. Okay, so here is the output from Jamovi, but SPSS will give you very, very similar output, right? SPSS fortunately does not put a 0 in front of the decimal point in the p-value. So our p-value is 0.018. Our decision rule is reject if p less than 0.05. 0.018 is less than 0.05, so we can reject the null hypothesis. Okay, next we want to look at the means so we can see what's going on. This was a two-tailed test. Remember, for SPSS, you'll want to look at the p-value under two-sided test or two-sided significance, right? Once we determine it's significant, we look at the means and we see that, as my students expected, the people who took the exam with no camera did better than those who took it with a camera. Now, these are fake data. I generated them. We'd have to carry out a real exam to know the answer to this question, or at least to gain evidence one way or the other. But in this example, we would say having a camera on matters. Students who did not have a camera on did better on the exam. This is your plain English. What about your jargon? For your jargon, you want to look at these different things, the p-value, right? The degrees of freedom, the t-value, and so forth. Participants who took the exam with the camera on, then we give their mean standard deviation, performed worse than participants who took it without the camera. We give the mean and standard deviation. T, degrees of freedom, parentheses, t-value, p-value, colons d, right? So refer to slides like this to know how to report the results of analyses. And thus we would then, in this case, draw some inferences and say, it might be better to have the camera off. And then we might think, but what if it's just that they're cheating? Anyway, I'll leave that to you to think about. And that's the end. If there are any questions, please post them in the free FAQ discussion.